Hello and welcome to lesson 1 of week 12. In this lesson, we are going to continue with the graph data structure and we are going to focus on the weighted graph. My name is Mildred. Last week, we looked at the graph data structure. We looked at how we can create an edge, how we add vertices to the graph, and also how we can use the adjacency list to have a vertex and then the list of adjacent vertices in a dictionary when we create our graph. How we can look at all of the nodes that are accessible or when we can traverse through a graph. We also looked at how we can detect a circle in a graph, and this week we want to enhance that to look at weighted graphs where we add weights to a graph to be able to solve the shortest path problem. Now, when we talk about a weighted graph, we mean a graph where each edge has a numeric value or a weight. This weight can represent the cost or the distance or the time or capacity or difficulty, and normally we have graph is represented by the vertex and the edge, right? And then for a weighted graph we add a weight. Now the weight assigns real values to edges. Let's say for instance we have point A, we have point B, we have C, let's use uppercase, and point D. Let's say these are cities and we have a connection or an edge from A to B, B to C, B to D, and we'll say we want to go from A to D. Now these have weight. Let's say the weight is a distance, and let's say we have the weight here to be 3, and then we have a weight here to be, let's say, 2, and then we have a weight here to be, let's say, 5. Now when you want to see the distance from A to D, you add all of this. Now in the shortest path problem is when you have different routes, maybe A, B, F, and you want to see different routes from A to D. Now this is just one. The shortest path will have the shortest total distance or the time based on what you are looking for. So let's look at how we can implement this. There are different types of weighted graphs. We have the directed weighted graph where the weights are applied to the directed edges, so we have a direction from A to B. And then on undirected weighted graph is when we don't have like a fixed direction. It applies to undirected connections, and then we have a positive weighted graph and a negative one. Now we use the Dijkstra algorithm to be able to solve the shortest path problem and for positive values, and then we use the Bellman-Ford algorithm when the weights have negative values. Now there are two algorithms that we use to solve the shortest path problem. The first one we're going to look at is the Dijkstra's algorithm. Dijkstra cannot handle negative numbers, and so we use Bellman-Ford algorithm to handle negative weights. Now for the Dijkstra's algorithm, we find the shortest path from a starting node to all the other nodes with no negative weight. So what it does is repeatedly selects the nearest unvisited vertex and calculates the distance to all unvisited adjacent vertices. And what we're going to create now is something that will calculate the weights, and so we'll always be able to get the shortest path. In Python, there is a module that we import called the heap queue. Let's say import. Now this module provides an implementation of the heap queue, and heap queue is the priority queue algorithm. And by default, the heap queue creates something we call the min heap. And the min heap is the smallest element is always at the root, like index position 0 of the list representation. So we're going to use this heap queue to see how we can implement a weighted graph. Now the idea that we use when we want to implement a Dijkstra's algorithm is to use the priority queue, which we'll use this heap queue module for. We want to maintain a table of the distance from each node. We want to greedily pick the next closest, that's the minimum distance node, and we want to update the neighbors' distances if a shorter path is found. Now, when we do this, we are going to see what the time complexity will be like. So, like we did last week, we'll create a class, and let's call this class weighted. Now, we want to create a init method here, and for this we'll just create a dictionary that will hold the graph. So we'll say self.graph is equal to an empty graph, and here what we want to do here is to store the adjacency list. That's what we'll use. Okay, now we want to add an edge. We'll add a vertex and an edge. Let's create a method that we'll use to add a vertex. So let's say def add vertex, and we want to put self and the vertex we're going to add. And so if the vertex is not in the graph, then we want to set that vertex as a key, and then the value is going to be an empty list, because we know for adjacency list we have a vertex as a key, and then we have a list of connected vertices as the value, like this in a list. So we'll store the value as an empty list where we are going to append the edges to when we are done. So we'll say if not, so let's say the vertex v not in self.graph. So if it's not in the graph, we want to now add this to the graph. So self.graph v, so the key should be equal to an empty list. So now when we're adding edge, we can now add the vertex here. So let's say we add the edge, and for this edge we want to add the first vertex, second vertex, and then we have the width. Then we set the direction. So by default, let's leave the directed to be false, and so we can set it to true when we call this. So let's say we'll represent the first vertex with u, the second one with v, and then the width. Then let's set a call directed and set it to false, so we can use this to see when we are doing a directed and an undirected graph. Now we want to add the vertex here, so we'll add the u, so we'll say self.add vertex u. So we're using this method to add the vertex to the graph and set an empty list of adjacent vertices that we're going to add later. So self.add vertex, and we're going to add. So now the vertex we added, u and v, they are both keys. So what we'll have is we'll have u and we have an empty list, and then we'll have v, and then we'll have an empty list. So this is what we have now added there. Now when we do this, we want to append the second vertex now and the weight to the graph. So where are we appending the second one? Well, this is the key. So what we have is u, right, and then we have the value to be a list of empty adjacent vertices, just a list that will store all the adjacent vertices. So now I'll say self.graph. Now because I added u now, so I'm going to say self.graph u. I'm using the key, and I want to append to the value of that v and the weight w. Right now, because this is the first thing we do, and if this is a directed graph, right, and this directed is set to true, which means if it is directed, this is just going to do this just one direction, right? But if it's undirected, then we want to make sure we also append for v. So we have v here, and the value is an empty list for now, so we want to append u and the weight for v. So now let's say if not directed, then we will append self.graph. Okay, so if we leave this as false and don't set it to true, we'll append v.append, and now we're appending. Okay, so now we've done this, we know we can add a vertex and an edge. Okay, so in the example we did in the live web conference, where we try to create like a transport network analyzer, where you want to add all of the different stations or train stations or so all of this will be the edge that we are adding to it. Now let's implement the Dijkstra algorithm, so we can look for the shortest path or the shortest distance between two paths. So let's say depth, I'll call this Dijkstra, and we want to put the start, right? We're looking for the edge we're starting with, and then we're going to look from that edge to the other distance. So let's call the variable distances, and the value here, let's use this to say node, let's say float infinity .in for node in self dot. Now let's set the start. So let's say distances start is equal to 0. Okay, now we talked about the priority queue, and we use the heap queue module in Python to get that. Now we want to set the priority queue to be the distance and the node, right? And so the distance that we have, the first distance, we're going to use the start, the index position start will be equal to 0, right? So let's call it priority queue pq is equal to, we have the list of the distance, which is 0, and then the start node that we'll start with. So this will have like distance and node, and then we want to say while priority queue, we want to set the current distance and the node, and then we'll use the heap queue module to pop and store it, because we are using that queue. Let me write it to say like while pq, we'll say current distance node is equal to heap queue dot heap pop. So you have to read about the heap queue module and see the different methods or functions that you have when you use that module. So we'll do heap pop, and we're popping pq. Right now, if the current distance is greater than the value for this distances node, we don't know the node here now, because we'll just call this function to work on any node. So we'll say if current distance is greater than distances node, then we want to continue, right? And now we can now look at the adjacent vertices, and let's use an iterator. I'll call this iterator neighbor. So we'll say for neighbor weight in self.graph node, we want to say the new distance is equal to, let's call this new distance so it will be easy to write, current distance plus the weight. So you see the whole idea where we say we use a priority queue to get the mean heap. We maintain a distance table. We readily pick the next closest or the mean distance node, and then we update the neighbors, which is what we're trying to do now. So we'll say the new distance is current distance plus the weight, and we'll say if the new distance is less than distances neighbor, we want to now say distances neighbor will be equal to new distance, and then now we can call the heap queue. So we'll say heap queue dot heap push pq, and then let's say new distance will be the new vertex, and then the neighbor. So we'll update the weights for the neighbor. So once this is done, let's return the distances. All right, so let's try to test this and see if it works first before we know whether we are correct with this, and then we'll move into looking at how we handle negative weights. So let's say if name equal to main, then we'll say g is equal to, we want to create a graph, so we'll say weighted graph, and we want to add the edge, so we'll say g dot add edge. Let's add an edge, we'll add a, b, and then we'll add the weight. Let's say the weight is 1. Let's add edge a, c, and let's add this with 2. Let's add edge b, c, and 1, and let's make here to be, let's say this to directed is equal to true, and we'll add, let's say c, d, and 3. Right, then let's print out this. Let's say print g dot Dijkstra a. We're going to be getting the shortest path from a, so we want to output the shortest path from a. It should print out something like a0 to b1 c2 d5, and so, because when we get from a to a0 to b, the weight 1, to c is going to be a to c2, and then to d we are going to add 1 plus 2 3 plus 1 4, and then it's going to be to d will be 5, because you're going to a to c is 2, so from c to d is 3, so 2 plus 3 should be 5. So we should get 0 a to b, a to a0 to b1 to c2 and to d5, and so if all is well, that should print out. So we have an error here for the spelling of neighbor here. So I have neighbor here, so I have this neighbor spelling. So there's British and there's American spelling, and so unsupported operand current distance plus weight. Where did I have that here? So new distance is equal to current distance plus weight. So there is something that is not correct here. So the error here is when we appended this, it's supposed to be we append vertex 2 and the weight here will be vertex 1 and the weight not with vertex 2. So this is where the error came from. So let me clear here and run again, and we have it working. So we have the distance from a to a is 0, a to b is 1, a to c is 2, a to d is 5, because what we put here has the start is a here, and when we see here the weight here from a to b is 1, from a to c is 2, which means from a to c is going to be 2. Then from b to c is 1, which means from a to b is 1 and b to c is 1, so a to c will be 2. And then when we have a to d, a to c is 2, right? And then we have c to d is 3, so 2 plus 3 5. And so that's how we calculate this with the Dijkstra algorithm. Now when we want to order the nodes in this algorithm, we use something we call topological sort. A graph that has a circle cannot be sorted, and in the next lesson we are going to look deeply at topological sorts and the Kant's algorithm that we'll use to implement this to see when a circle is detected, and how we define the directed acyclic graph and what we can do to sort a graph that the origin of the node is a directed acyclic graph. So you always find something we call DAG, and that is what it means. So thank you and see you in the next lesson.